Okay, so I've already done the welcome, but welcome again, everyone, to the KELVAR workshop. Great to have you here. Great to see new faces and colleagues that we've met with previously. So I'd like to hand over to Julian Radu, Harvard University, world expert on AR and education, for the keynote for this talk. So hopefully Julian's ready to go.
I am. Thank you so much for the introduction. Can everybody see my slides? Let's see if I go into full mode. Let me see if I can show the videos here. I'm going to try to have the Zoom open while I'm in presentation mode. Can everybody see my slides if it's presented like this? Everything comfortable?
Yes, it's good.
Great, perfect. So thank you so much. I'm actually honored to be invited to give this keynote by the other organizers. So really happy to be here. So I'm a principal research scientist at the lab in the Harvard University Graduate School of Education. And my work includes looking at augmented reality in makerspaces and generally at XR in educational settings. And so in this talk, I will present you some of the projects I've done with my collaborators and also some of the lessons that I've learned. And I'm hoping that by the time we finish here, I will have taught you how AR can be both helpful and also damaging to learning, how AR can impact people differently depending on the team roles and the collaborations that they have. Also, I would like to tell you about how AR failures can reveal better non-AR educational ideas. And also, I want to talk to you about the importance of decomposing learning components of an AR experience and how that process can inform better design. And the reason why I'm interested in these things is because there's lots of excitement about XR, but from me and my perspective, talking to educators, as a researcher, I find that there's quite a bit of resistance and skepticism from educational organizations. And this is because AR provides some barriers to entry and access. So for example, here I have a picture of two people using augmented reality headsets to learn about physical objects. But these headsets are actually quite expensive. Like the hardware that's on their heads is probably close to between $5,000 and $10,000. So it's quite prohibitive right now to have these kind of devices in schools. Obviously, even if schools have them, they might not be able to have them for every student. So there's kind of a barrier of entry and access to this. There's also high costs, not only of the hardware, but also of developing these kind of experiences. They can range from tens of thousands to hundreds of thousands of US dollars. And so that's because these experiences are usually quite complicated. Like you have to create 3D models, you need artists to be creating this, you need programmers to be creating the interactions that a user might have with the learning content and the simulations. You also need to be collaborating with teachers and other educational stakeholders that can understand how an AR experience will unfold. So all of this is quite costly to develop. And it's also, there's still quite a lack of familiarity with designing these kind of experiences for people that have not seen or worked in these kind of spaces before. So for example, talking to educators, it's kind of difficult for them to design and think about how these experiences would happen. So I just wanted to take this opportunity to talk about how we as researchers, we need to present our research findings in quite a detailed format so that we can be useful for educators and to kind of convince educators to adopt this technology in educational settings. So I wanted to present some critical questions that might be useful for you as you think about evaluating augmented reality and in general XR experiences. And I will do this based on the projects that me and my team have built. The kinds of things we do with my team is we work in maker spaces. So these are environments where people are, so there's a bunch of students and they're kind of collaborating and building physical objects. And these kind of objects are usually involving electronics or things where once you've connected them properly, they are doing things, but you cannot see what they are doing by just using your naked eye. And so augmented reality is actually really helpful in these settings to help people to understand what's going on behind the scenes with these kind of projects. So one project that I wanted to show you is this speaker. So this is actually a working speaker that's kind of been exposed a little bit so that students can explore different parts of it. This process happens in your headphones. It also happens when you're listening to TV, and it generates sound. So basically, sound is coming from this smartphone that is plugged into the system, and then electricity is being converted in different ways and amplified, and then it's being converted into magnetic fields and also movement of this membrane over here that produces sound. So actually, if you play sound through this system, you hear the sound with your ears. And what we explored is how can we allow learners to be able to look at this object and explore this object using augmented reality headsets so that they can learn about it more easily. And so you can see here that on the left is the object by itself, and on the right, it's the same object, but it's seen through an augmented reality headset. And we basically run an experiment to try to understand what are the differences between these two conditions and how does augmented reality influence the way people learn and communicate to each other. And so I just wanted to show you what this looks like. Let's see, these Zoom controls might get in the way. So the way the system looks is when you push on, so when you look at it through augmented reality, you can push buttons and in order to watch how it plays sound. So you can see these visualizations of sound that are coming out. You can see visualizations of magnetic fields in the middle here. You can also see visualizations of electricity on the left side here. And it's interactive in that you can move around and you can spatially see how the magnetic field looks like in 3D. But you can also physically push buttons and you can see that the physical object is being pushed and pulled by the magnetic fields in response to how electricity goes through the system. And as a user, you can also, so not only can you look and see all these visual representations that are kind of linked together to your actions, but it's also physical in that you can reach in, you can grab this object, you can move it around, and as you're doing this, the simulation is changing in real time to adapt to how you as a learner is interacting with the physical object. So we built this in the hopes that learners their learning is going to be enhanced. And indeed, it does happen that their education is enhanced when they interact with this object. But I think a critical question to ask whenever you see AR experiences is this experience actually bad for learning? Because something you might see, so in this case, I am showing a graph of, on the top, it's a bar. The red bar is the augmented reality group of students, and on the bottom bar is the non-augmented reality group of students. So we had sets of students exposed to each of these conditions. And it does turn out that the AR people learn better than the non-AR people. Although it's kind of interesting in that they're both learning quite a bit, but the AR seems to be helpful. So we could stop here, but I think it's really important to ask what's going on behind the scenes and actually for what topics is the AR useful and for what topics is the AR not useful. So I'm going to move this down here. So it turns out that for understanding, for example, the shapes of magnetic fields, you can see that the augmented reality was quite helpful compared to the non-augmented reality. For helping people to answer transfer questions and thinking deeply about relationships and applications of these concepts, the AR was extremely helpful compared to the non-AR. But for some things, it wasn't so helpful. For example, for understanding movement in relation to the electricity or how magnetic fields are related to electricity, the differences between the AR and non-AR group weren't that high. And it's actually really important to ask what might have been not so helpful for the AR group. So we actually also measured other learning concepts, and it turns out that for the AR group, they learned less well about how the amplifier works in this system. So we had an actual switch in the background that changed the amplification, and the people who didn't have augmented reality learned better about it. Also, understanding kinesthetic things, like how magnetic fields influence the movement of objects, it turns out that the augmented reality group performed less better than the non-augmented reality group. And so this, I think, is a really critical finding because the augmented reality seems to be worse. So we could have just given people the non-augmented reality apparatus and they would have learned better. And so it's really important to ask, why is this? So first of all, it's an important question to ask, for what kind of learning topics is the augmented reality bad for students compared to the traditional ways? And then it's important to ask, now that we understand that some topics are helped by augmented reality and some topics are helped by not augmented reality, how can we sequence the learning activities so that people see augmented reality to learn about some things, but then we hide the augmented reality so that they can focus on other things, such as the kinesthetic aspects of the experience. So for this kind of question, it's really important to understand, could this experience have been bad for learning? And it turns out that something like this can be good for learning when augmented reality is involved, but augmented reality can also be detrimental to learning. Another question that's kind of related is, does everyone actually need augmented reality? So this is another example that I wanted to show you, in which we've taken a robot. So this is a robot and it has different sensors on it. So in the front here, there's a proximity sensor, there's another sensor on the left. And people usually see this on a computer screen. So as my hands are moving, you can see that the sensor values are changing on a computer screen. And so in order to see these sensors, you would be looking at a computer screen while the robot is moving sort of separate from the computer, and you'd be able to understand how these sensors are connected. So we're trying to figure out, when we show augmented reality, how does this change the learning experience? So we built this augmented reality visualizations where you can just look at the robot, understand these sensors as you're moving the robot in space. And so these sensors are overlaid. You don't need to look at a computer screen anymore. And what you can do is you can also run the robot in a real situation and just be watching the robot as it navigates around this maze, and you can see the sensor values changing in real time as it moves around through a physical environment. And so we were interested to know, when we give people these kind of visualizations on this robot, how does this change the way they learn and also the way they collaborate with each other? So again, just like in the previous study, we had two conditions. We had a condition in which, so this was a 2-participant study. And in one condition, both participants wore augmented reality and they saw the robot with the sensors. They could also see the sensor values on the computer screen. And in the other condition, it was non-augmented reality. So they couldn't see sensors on the robot, but they still saw the sensors on the computer screen. And when we looked at the learning gains, it did seem that augmented reality helped with the learning, but it was really interesting to investigate for which of these students did the AR actually help. So it turns out that for the participants who are closer to the computer, the AR makes no difference. So if you give these people augmented reality visualizations on the robot, or you don't give them this technology, they are learning the same. While for the other person, the augmented reality made a huge difference. So they actually started a little bit lower than the other participant, but with augmented reality, their scores and learning was boosted quite significantly. And so there's something interesting that happens here, which is the fact that augmented reality is influencing different people differently, depending on their access to resources and also their roles and the kinds of things that they are doing in the activity. So from an educational perspective, it's important to ask this question and figure out, okay, so for this context, when people are doing this thing with these robots, for which of them is it really important to give augmented reality? Because it might turn out that in a classroom, you might have limited headsets. So in this case, for the person who is close to the computer, they don't actually need a headset. They're just learning in a similar way. But for the other person, the headset is helping them quite a lot. And it does turn out that the headset is actually helping both students when they start collaborating and communicating with each other. They have a sense of like better teamwork, and they make better progress on the problem-solving activities. So it does change their collaboration quite a bit, because now both people are learning and engaged in the activity with augmented reality. So that was the question of, does everyone need it? And it turns out that sometimes not everybody needs it. Another question is, are there easier ways to do the same thing? So this is, oops, I'm just going to skip here. We were interested to know, can augmented reality help with understanding of circuits? And so here I have a circuit. There's an LED. There's actually two LEDs, one on the left and one on the right. But this one on the left here will be blinking. And so this is a blinking circuit that is sort of a popular thing that gets built by people who are just learning about electronics. And the way this LED is blinking is it's influenced by this knob over here. And so electricity kind of passes through these wires and it influences how fast the LED is blinking, and it's generating basically a blinking signal. And we wanted to help people to understand what's going on inside of circuits like this. We wanted to design a platform where people can easily kind of bring these circuits into an augmented reality environment and see what's going on inside of them. So we designed this. This is called a holographic breadboard, where it's basically a holder and it's got these graphs attached to it. And so a student can take a circuit, plug it in here, and once they connect it, they can see the signals measured at different points wherever they're plugging in the wire. So now they've plugged in this wire into probe 1. And so now probe 1 is going to show how this LED on the left side here is blinking. And so the system is basically just measuring the voltage and displaying it on there. And so this is an easy way to measure signals from an ongoing circuit. And the interesting thing here is that this circuit, the blinking rate, is influenced by a capacitor that's charging and discharging. So this other probe was connected to it, and you can see that when it's charging and discharging at a certain rate. And on top here, you can see both signals connected to each other. So the blinking is actually influenced by the charging and discharging of that piece of the circuit. And by turning the knob, you can sort of influence the rate at which the blinking happens. And then you can sort of experiment with different settings and how the charging and discharging is influencing the signals at different points in the circuit. So we built this and we were really excited. So we were like, okay, we can put augmented reality in a makerspace. We can allow students who are building circuits to bring their circuits into this platform. And then they'll be able to easily see their signals and debug their circuits. And we deployed this in a classroom of students who was just learning about circuits. And this required having a computer in the classroom and also a HoloLens headset attached to the computer. And it was really interesting because what we found is that the students didn't really want to engage with this platform on their own. And the reason is actually multiple reasons. So one is it was quite complicated to get the system running. So people had to bring their physical circuits from the desk where they were working. They had to bring it into this space where the computer was. Then they had to follow, this is a poster that we had on the wall. So they had to follow all these instructions first on how do you log into the computer? How do you start Unity program? Once you're in the Unity program is running, you have to put on the HoloLens. You have to figure out how to do gestures in order to activate the menu and the applications. There's like a lot of instructions. So there's a barrier to entry there, but then there was also another barrier to entry, which is the fact that the way this breadboard is, the way it was designed is that this 3D printed orange holder is made for our type of breadboard. And if people, when people are making circuits, they might not work with this type of breadboard. They might also have a bunch of wires and things on their desk. So it's kind of inconvenient for them to move and come in here and get hooked up to this system. So basically, we found out that the barrier to entry was too high, and the students didn't really want to engage with this just because it was so complicated, and they didn't feel like that effort was warranted in order to get access to these signals. So what we wanted to do is we basically tried to understand what's useful here, and can we give it to students in a different form that doesn't require all this augmented reality and computer hardware. So what's important here is that it's easy to access, like somebody can just plug in wires into their circuit, and also they can see signals quite directly while they're looking at their circuit. And so what we ended up doing is we built this other tool that is a not augmented reality experience. Sorry, I'm just forwarding through this video. Let's see. So we built this handheld tool that's basically something that you can just plug in, and it has a little display on it. And the display can show you, it's an oscilloscope that is really simple to use. You can just plug it into the circuit, and it just shows you what's going on at that point. And you can see it's live. It's basically showing the same information as the augmented reality, except that it's one display instead of all those multiple displays. But it's much easier. And from a student perspective, it's much more direct and easy to use wherever the students are. So this is an example where we basically took something that was working in augmented reality, and we identified what the blockages were, and then we figured out how to convert it into a form that's much easier and much cheaper. So this is probably less than $20 to build, whereas in the other case, you needed a computer and you needed a HoloLens and you needed all this hardware. So this is an example where by failing with an augmented reality experience, you might find that there's other non-augmented reality possibilities that you can do more easily and more affordably. And so that was an easier way of doing the same thing that the augmented reality was doing. And another way to kind of get at this, so one way was we just kind of failed at our augmented reality experience, but another way is to think about the augmented reality experience and break it down into the components that are causing the learning. And if you can understand that, then you might be able to design better alternatives. And this is the last project that I want to show you. It's basically a physics phenomenon that happens when you drop magnet into a coil of wire. So it turns out when you drop a magnet in a coil of wire, the magnet slows down. So the coil of wire kind of repels it. On the left side is what you would see when you were doing it physically. On the right side is how people learn in a classroom setting. They just kind of learn from these figures. And so we're trying to understand if we combine both of these, can we help students to understand it more easily? And we ran an experiment in which there's an instructor interacting with a student. This was last year, so our school was closed, and so students were doing everything remotely. And so we did augmented reality remotely by having, so the instructor was myself, and I was working on my desk with physical objects, and I was wearing an AR headset that was doing screen sharings to Zoom. So a student who's connected into Zoom was able to see through my headset at the objects that I was interacting with. And I just want to show you what this experience looks like from a student perspective. And I'm actually going to kind of walk you through this. So there's some physical objects here and virtual objects. So there's a physical magnet and a physical coil of wire. And then there's some virtual things that as an instructor, I can see through the augmented reality headset, and the student basically gets to see this whole thing while talking to the instructor, so talking to myself. And so what happens here is that you have a magnet, and it's got two poles, and the magnet itself has a magnetic field around it. And so when you take this magnetic field and you bring it close to the middle of this coil, the magnetic field basically is going to intersect the coil. And as you bring it closer, you can see that the magnetic field lines are crossing into there quite strongly or quite weakly, depending on the distance. And as an instructor teaching students, I can say, well, look at this. The change in magnetic field over there, right now it's not changing, but if I bring the magnet closer, there's more magnetic field. If I bring it further, there's less magnetic field. And I can also show the fact that when I bring this magnet in, there's electricity that actually flows through this coil of wire. And because of this, there's some laws in physics which indicate that when there's electricity flowing, there's a magnetic field that gets created in a certain direction. And so because there's this magnetic field that is opposing the movement of my magnet, the coil is basically repelling my magnet. And so let's see. So when I move this magnet in, the coil is basically creating an opposite magnetic field that is pushing my magnet away, or it's pulling it back if it goes further. And so with the augmented reality, as an instructor, I'm basically explaining this to a student who's watching, and they can stop me and ask me questions, and we can use these visualizations to explore the learning material through visuals. And there's also other visualizations we can show, for example, the fact that when the coil is creating a magnetic field in a certain direction, it's as if the coil was magnetized with a magnet, with the north end pointing at the magnet. And so you can see there's all these visualizations that are changing in real time as the instructor is talking to the students. And so we ran the study. We also ran it in two conditions. So the high AR condition was what I've shown you. And it has all these visual representations. There's also a low AR condition in which we just showed them a simple representation of a kind of a block on top of the magnet and a block on top of the coil. And then on the left here, there was a visual representation of what a magnetic field looks like, but it was never changing. So it was as if there was a piece of paper here. And I kind of wanted to tell you about what happens in the low AR condition, because we got these very excited student comments like, I liked it, I thought it explained things much better. They really enjoyed that it was useful to see it interactively and also in real life. So students were really excited about the fact that they could interact and talk to the instructor. Also the fact that in the future, when they take the test, they will think back and kind of imagine what they saw. And some of them felt like they had to do less mental labor just because we were talking and doing these movements. And so we were trying to think, for this non-augmented reality condition where you don't really have a lot of augmented reality, why are these students still being influenced, and why are their learning gains still pretty high? So it turns out that there's quite a few educational components of just this experience. So one is there's verbal interaction and feedback that they get from talking to the instructor while doing this activity. There's physical objects that are visible here, and there's explanations that the instructor is giving just with their voice, even if they're not seeing any other AR visuals. There's a lot of explanations being given. Also, there's this information about the magnetic field on the left here, so they can easily remember what a magnetic field looks like. And then it's also novel. There's quite a bit of novelty because there's this new technology being taught over Zoom. But from the perspective, so all of these things can be contributing to student excitement and student learning, but from the perspective of just what is causing the learning gains and how is augmented reality impacting these. If you think of a non-augmented reality experience, actually you could do this without augmented reality. So for example, if I had just a piece of paper on my desk that showed what the magnetic field looks like, and I would just be moving these objects around, the student would still get verbal interaction and feedback from an instructor. There would still be physical objects involved here. They would have information about what a magnetic field looks like because it's printed on a piece of paper. The only thing that the AR seems to be adding here is just the novelty of the technology. So it's kind of important to decompose these experiences so you can understand when students are learning, why are they learning? And obviously in the AR condition that had more interactive visuals, the same components are present as in the lower condition. But now you have more things like these representations that I showed you in the video are dynamic. So they're changing in real time. They're animated. They're also, some of them are 3D, so you can kind of understand how they happen in space. And they are also interlinked with each other. So when the magnet is moving, the electric flow of electrons is being showed, but also a graph is changing at the same time. And so all of these reasons might account for why students are learning. And so I think it's really important to understand not just the fact that students are learning better in the AR condition, but why. Which of these specific things are causing and contributing a lot to the learning? Because once we understand that, we can actually design better experiences. And so the way we're trying to answer this question is by looking at the sequence of questions that's being asked by students and to see kind of like which of the questions are triggered by, like, what are they actually paying attention to when they ask a question, and then what else do they look at in terms of the visuals, and how does that change the way the questions are asked? So this diagram is just a quick kind of preview of how we can do this kind of analysis to find out which of these is causing more of the learning gains. But I think it's really important to understand, to sort of decompose these experiences, because there's lots of components to them. So I just wanted to close by reiterating the questions and the takeaways. So the first one is this experience bad for learning? And it turns out that in order to answer this question, you need to have multiple measures of learning. And you might find out that AR can be helpful and detrimental for some things. And it's really important to be critical about it, because then you can approach educators and say, well, for the thing that you're trying to do, AR might not be the best. You know, there might be some cheaper or lower cost alternative. Another question is, does everyone need it? And it turns out that AR can impact different people differently, but it might not be needed for everyone. And also it might not help everyone equally. Then there might be other ways to do it. And especially if your students aren't reacting so well to AR, then there's a question of, is there another better non-AR idea that could work for the students and it would be maybe cheaper to use? And I think underlying all of these, it's important to understand what parts of the experience are causing all these learning gains. And so decomposing these experiences and analyzing the specific parts of them are important because they can help you to better design, but also better communicate to educators. And as a community of researchers between us, we can better document the benefits and the detriments of this kind of technology. So thank you for your time. All of these people have been really wonderful in terms of collaborating and contributing to these projects, so I just wanted to acknowledge them. But thanks for listening, and I will take questions.
So are there questions?
And sorry, feel free to, somebody should tell me if there's questions in the chat or in the Discord. Feel free to kind of bring them up.
Well, we've got 5 minutes for questions. So are there questions in Discord?
There aren't any right now.
Okay, well, we'll take questions from the group on Zoom then.
There's already a question in the chat.
Great.
Asking where we can access the presentation. Will you share this presentation, Julian?
I can share the papers, the projects of this presentation. Yes, I can. I might have to edit this presentation a little bit before sharing because some of this has not been published yet. So if I do, I'm definitely happy to share the papers of the projects that have been published with this research.
Won't the recording of this video be made available by IEEE VR?
And we can do that too.
I think that, I mean, sorry, that I just wanted to say the
that's perfect also.
Are going to be made available.
And maybe you could put your takeaways in the Discord, or I can try and copy some of those in there.
I might be able to just actually copy and paste them in the Zoom chat. I believe there's some other questions from people raising their hands.
Yes, yeah, please go ahead. I don't know who's first.
I don't know if I'm asking out of turn, but okay. So one of the questions that actually was posed to me by a NSF program chair was, is there a systematic approach? Is there a formal approach to studying, what is working best for the students, what's not? Do you use some sort of ethnographic approach? How do you derive useful data? Like you said that, for instance, one of your takeaway messages is to really understand what works and what doesn't work. Is there a systematic framework, formal method by which you go about studying that from your interactions with the students?
So I think that's a kind of a complex question to answer because there's multiple ways of getting at that. The way we've done it that has been kind of the cleanest is to do these very controlled studies in which we have different conditions, and for some conditions we kind of just focus on one of these variables and try to differ it from the other conditions. So for example, in the speaker study that I showed you, I actually only showed you the AR and non-AR results, but actually within these, we actually have multiple conditions in order to help tease out not just the presence of these visualizations, how it's influencing, but like, is it the novelty effect or is it the scaffolding, like the timing of things? So one way is to have multiple versions of the software and measure the differences between them, but the versions of the software have to be carefully chosen so that it's not just like augmented reality versus a textbook. Because in that, or a website, for example, because in that case, there's quite a lot of differences between them, and you might not be able to argue specifically which component is causing it. So having multiple conditions is good. Another way that we've started to experiment with is this more qualitative analysis of having like a framework that explains the depth and the types of questions that they ask, and then analyzing how does the AR influence the sequence of questions or the probability, like the percentage of each question, like the amount of each question that students ask, especially as they look at the parts of the AR visualization. So you can do more of an ethnographic qualitative analysis of their discourse to try to understand how the AR is impacting the way they're thinking and the way they're communicating and their attention. And we also had, I think it's really also important to collect a lot of data about the participants themselves so that you can do more look at individual differences to find out, for example, for the people who came in with a little bit of knowledge versus the people who came in with a lot of knowledge, how does it impact them, for example? So to tease out apart, how does it impact different people, but also how does the different components impact their the learning? So hopefully that kind of gave you some direction, but I haven't seen any kind of big systematic framework of doing this across.
Yeah. The reason I asked that methodological question is because the type of research that I do often is carefully controlled experiments in a lab. So and what I observe you doing is sort of studying how students actually learn in the context of teaching them at the same time, if I understood this correctly. And so that's sort of a very different, nuanced approach to me. And in the context of that, that's a bit of a kind of like a study in the wild, so to speak, while you're, providing the intervention with the student. And so that's why I was curious, how do you go about systematically studying what works, what components don't work, what components do, as compared to the carefully controlled approach. Thank you.
Yeah, I feel like it's easier to study these in a lab setting, or like when you have an instructor who is going to be kind of precise at giving the same information to students, versus in a classroom, it's quite messy. There's so many variables that are at play.
Thanks, Julian. Can we all thank Julian? We have little kind of claps, I suppose. Hopefully you can clap on for a great keynote. We'll have time to ask more questions later in the general discussion section at the end of the workshop. But thank you so much. Incredible presentation.
You're welcome, and I'm happy to take questions also in like email format if you feel like sending them there. I know there's some people who didn't get to ask the questions.
Yeah, so apologies. You can hold those questions for the end, or you could email Julian or put them on Discord, and I'm sure he'll respond.
Yeah.
I want to call this, we're into the papers section of our workshop. We have 8 papers to get through with a break in the middle. And the first paper up is Improving Language Learning by an Interact to Learn desktop VR application. So could we ask the presenter to please share their screen? Thank you. Thank you, Zan.
Hello everyone, I'm Liu Xiao. I'm going to talk to you today about a recent study by our group. I'm sorry that my oral English is not good, so I recorded into a video advice. Combined with subtitles, I think you may understand it better. So let me play the video. In this video, I will present our preliminary empirical study on interactive activities in a desktop virtual reality environment. Improve language learning by interactive desktop VR application, a case study with Painter. For most second language learners, mastering vocabulary is not an easy task. They spend a lot of time understanding and memorizing English words. Evidence from embodied cognition research on language processes suggests that the learner's bodily sensations and actions can enhance comprehension. Some studies proved that well-designed non-immersive desktop VRs could be conducive to learning and training. The desktop VR may provide learners with rich scenarios and interactions to promote understanding and memorizing words. So we propose a desktop VR application for vocabulary learning called Painter. The purpose of Painter is to inspire and engage second language learners with interactive activities to build their vocabulary of colors. Painter consists of a lecture video on the left and an interactive 3D space for painting on the right. The lecture area explained each English word and illustrated its origins, usage, and examples. Visual materials offer the key points and illustrations of the color. In the interactive area, learners can paint the objects on or after lecture watching, pressing the buttons of the color, activate color selecting and word pronouncing. The learner can control the play of the video through the UI. The instructor's video is not pre-recorded but generated automatically by an engine based on text-to-speech and lip synthesis approaches. This engine generates video by importing merely an image or a clip of human and text. When learners press the keys of W, S, A, D, or up, down, left, and right on the keyboard, they can move to 4 directions: front, back, left, and right in the scene, from a first-person perspective. In addition, they can use a mouse to hit and right drag and drop to rotate the object. We conducted a preliminary user study to evaluate patrons' effectiveness and learning experience in learning words. We recruited 6 college students aged between 22 and 23 to participate in the experiment. All participants saw colors normally. This study employed a within group design. All participants took part in 2 collisions, picture and non-real video collisions. In the picture collision, each participant was asked to learn 5 English words about color by watching a video lecture and painting objects in the scene in line with the theme of the words in desktop VR. In the non-real video collision, each participant was asked to learn another 5 color words, different from the picture collision, by only watching a video lecture. The order of the 2 collisions was counterbalanced with a 2 multiplied 2 Latin square. To ensure that all participants had the same level of prior knowledge, we tested them on a questionnaire before the experiment to see if they had learned the words, and no one knew these words. We measured the learning outcome, cognitive load, and attention to compare 2 collisions. We also collected the eye track data of picture to study how participants assign their visual attention. Finally, we evaluated the picture through self-report rating using 7 level Likert scales. These self-report measures include the perceived usefulness, perceived ease of use, satisfaction, user experience, and learning experience of the picture. Since the sample size in this preliminary work is not big, we present the results using descriptive statistics. The overall performance of tests under picture collision was slightly higher than that of the non-VR collision. As shown in the left figure, participants reported a higher intrinsic, extraneous, and overall cognitive load under the desktop VR collision than the non-VR collision. The right figure shows that participants were more able to concentrate when studying under the non-VR collision. The table on the top right shows the results of eye track measures. Participants fixating longer and fixating more time in the interactive area compared with the video area. They also revisited the interactive area more. These results indicate that participants spend more time interacting than watching the lecture video. We evaluated pictures through self-report rating using 7 level Likert scales. Picture received a media above 4 as shown in the bottom right figure. The results show that participants found the picture interesting and liked this desktop application. Additionally, they thought that the interactive environment that picture offered could enhance understanding and memorizing English words. In conclusion, we found that interactive activities provided by picture were beneficial for second language learning, but supporting interaction and instruction simultaneously may split attention and overload the learner's visual, auditory, and motor channels. This is a work in progress and a small sample size limits the work, so we still have a long way to go. In the future, we will continue to move along this line and conduct an extensive study with significant sample size. We plan to focus on integrating interaction and teaching in an educational VR environment. And we will investigate how such desktop VR supports learning considering learning style. Thank you for your listening. If you have any questions or suggestions, please contact Zhou Yun. In this video, okay, that's our group is doing. Thank you for listening. Do you have any questions?
So I have a question, Zhao. In terms of the cognitive load issue around interaction, do you plan to adjust the application that you've developed?
Sorry.
I'll put that in the chat. Will I put it in the chat? The question? I'm asking about the cognitive load issue. If you could discuss the cognitive load issue.
This is in line with the previous finding where for educational purpose, which indicates that such learning environments result in increased cognitive load. More interaction requires participants to use more cognitive load, cognitive resource to process information. That's all. I'm sorry.
That's okay. Thank you. Are there any other questions? Well, I'm sure Zhao could answer some questions in Discord if there are any, or at the end of the session when we have our general discussion. But thank you for a very interesting presentation. I commend you.
Thank you. Thank you.
Thank you. We now have our second paper towards VR simulation-based training in brain death determination.
Yes, Erica. Just to introduce myself shortly, I'm Pascal. I'm a computer science PhD student from the University of Münster in Germany, and I'm happy to be here. We also decided to pre-record our presentation, so I'm going to share this quickly with you. Just a second. I hope I've selected sound. Okay. So I would like to present you our paper titled Towards VR Simulation-Based Training in Brain Death Determination, in which we created and evaluated an initial application prototype for virtual brain death diagnosis. To motivate our work, I would like to give you a short introduction to the current developments in the medical curriculum. In recent years, a paradigm shift could be observed here. While the knowledge transfer was the main focus for a long time, it is becoming increasingly important to teach students practical skills at an early stage. But this also introduced practical and ethical challenges. For most of the time, the students therefore are only allowed to take on the role of the spectator. But since it has been shown that self-involved learning experiences are very important for lifelong self-regulated learning, many medical curricula started to incorporate some sort of hands-on events. These training experiences mainly rely on mannequins, phantoms, or actor-based role-playing scenarios. The right side here on this slide shows the preparation and makeup of an actor, followed by the role-play scenario in which the student examines a patient. But let's take a look at the current status in the area of brain death diagnosis teaching. First of all, the topic of brain death diagnosis is very important because, especially in small hospitals, patients with severe brain damage are very rare. So local doctors develop a fear of some sort of making the wrong decision due to lack of experience. Therefore, many patients are not even examined, which leads to a shortage of urgently needed donor organs. Therefore, it is very important to train not only the theoretical aspects, but also the practical steps. The goal is that students should gain their first experience in the field of intensive care medicine, in which emotional factors, stress, and associated decision-making situations are very important. In the current medical curriculum, the practical part is often trained using a medical mannequin, as shown on the right here. But as you can already imagine, this current form of teaching has some limitations. In general, puppets are expensive and offer only limited response capabilities, leading to the fact that in the context of brain death diagnosis, the decision-making situation for the student is completely omitted, since the condition of the mannequin is already predetermined. Actors, on the other hand, are very well suited for role-play scenarios, but they are expensive, require elaborate makeup, and bring new ethical boundaries. They are not suitable for the practical part of the brain death examination. So, what is a possible solution? We think that virtual reality offers a great potential for complementing the traditional teaching methods of general medical education. Unfortunately, so far there are few experiences and evaluation reports when it comes to practical use in teaching with hundreds and hundreds of students per semester. So the goal of our project is to serve as a first step in this direction. A first visual impression of our scene can be also be seen on this slide in direct comparison to the original mannequin room. In terms of development, our prototype has been developed in Unity and currently fully supports the Valve Index in terms of hardware. For our setting, we recreated an intensive care room together with all the necessary equipment for brain death diagnosis. We also integrated the Pulse physiology engine into this project to be able to correctly calculate and display the patient's vital signs in real time. This also allows the user to receive appropriate feedback during examination. Furthermore, our prototype is customizable so that a separate scenario can be created for each user, making the decision situation more realistic and difficult. But to demonstrate our application, I would like to introduce you to some of the necessary tests that the user needs to perform during the examination. So, in this first example, the user tests for any pain response by rubbing the sternum and pinching the septum in the second step. So he's grabbing the tweezers and pinching into the septum. The second test I want to show you is the pupillary reflex test. Here the user has to illuminate both eyes and look for any pupil contraction. In this case, the pupils both contract upon illumination. The next test is the corneal reflex test, where the user uses a cotton swab to try to mechanically irritate the cornea. In this case, you have to look out for any defense reactions of the patient, for example, some blinking. The fourth test is the pharyngeal reflex test, where you try to irritate the back of the throat with some wooden spatula, and you are looking for any gagging reaction. The next two tests are the ocular cephalic and vestibulo-ocular reflex tests, but here only one has to be performed. For the first test, you look for any counter rotation of the eyes upon sudden head rotation, which is also present here. And for the second test, the vestibulo-ocular reflex test, you have to apply cold water into the ear canal and look for slow eye rotation towards the cold source. And sometimes this is also happening with some sudden counter rotation of the eyes, which is also here present in this case. For the tracheal reflex test, the patient needs to be disconnected from the mechanical ventilation to insert a suction catheter into the endotracheal tube to mechanically irritate the carina. Here you look for any coughing response. Lastly, the apnea test is performed. Here you start with the pre-oxygenation of the patient, followed by the disconnection of the mechanical ventilator. So here we are going to pre-oxygenate, make sure that we have built up enough tolerance, disconnect the patient, and now we have to check the partial arterial CO2 pressure, and we wait until it reaches a threshold of 60 millimeters on the mercury scale, or the patient starts to breathe spontaneously. So we are here at a value of 51, but this drops down to 47 now. And if we now look at the thorax excursion, we can see that this patient started to breathe spontaneously. You can also see this on the respiration rate model. So for initial evaluation, we invited 3 domain experts to test our prototype. All of them had at least 5 years of experience in brain death diagnosis at this point. All 3 received a short introduction to VR in our tutorial scene before performing brain death diagnostics. Afterwards, a semi-structured interview was conducted in which we asked questions especially about display quality and immersion, as well as the medical plausibility of our simulation. Overall, there was very positive feedback except for a few comments. Our learning scenario was rated as appropriate given the learning objective. Problems typically arose in the area of haptics when it comes to interacting directly without medical tools with the patient's body. An example of this is eye-opening which is very challenging as there is no common hand movement metaphor for this among any medical professionals. So based on this feedback, we are currently in the progress of evaluating a slightly improved version of our prototype in the medical curriculum. Over 100 students are participating in 2 iterations. For the first iteration, we split the group in half. The first part takes the course in the conventional way. The second part takes the VR supported course. In the second iteration, both halves of the group are divided again, so that we end up with 4 constellations for evaluation. In terms of metrics, we are using the PANAS questionnaire, which is mainly used to measure the positive or negative emotional effect. And on the other hand, we are also conducting a learning review to investigate the long-term learning effect. All this is taking place in the so-called Limette, a circular complex of rooms divided into 12 small study rooms. Each room is equipped with a Valve Index VR system and can be monitored from a central observation room, which you can also see right here. So I hope I could give you a good insight in our paper, in our current work, and also in our current progress. Thank you for your attention.
Thank you, Pascal, for a very interesting and obviously very important simulation that you're developing there. Are there any questions in the chat? I'm just trying to have a look. People ask questions.
There aren't in the chat or in Discord yet.
Are there any questions from the floor?
Hey, I'll ask a question. Really amazing visuals. I was kind of wondering, as you're doing this, were there instances where the patient did have responses, right? Because I think that sort of that's the hard case where you have all the myriad of possibilities of them being responsive as opposed to not being responsive, which is just one.
Yeah, we have many responses, so we are not completely developed all the possible responses to all the reflexes. So cuffing and gagging are currently not implemented, but smaller things like pupil dilation or pupil contraction, reactions, vegetative reactions to pain responses like increased heart rates, etc. Are all implemented, but it's the hard part that's still in development for this.
Yeah, really nice work though. It's absolutely beautiful.
Thank you.
I'm wondering if you could. Sorry, there's a question. Sorry, go ahead.
Yeah, I had a quick question. I was wondering if in the future you intend to ever use more haptic gloves instead of remote controls, because I know that part of being a surgeon is being able to do those fine-grained movements, like don't puncture the ear canal, but you can't get those kind of fine-grained details in a remote control environment.
That is a good question, because it is important to have this fine motorics. In case of our learning objective, it is okay for now to have this not fine movements, just so the students are able to practice the steps and are having the first experiences with this topic. But if you could get a finer movement control for the hands, it would be very, very, very great. But for example, those Tesla gloves or some sort of gloves have the problem that what we are trying to achieve is that we want to have hundreds of students to take on this course. And these Tesla gloves are very problematic when it comes to cleaning and getting the hygiene right. So that is something we are currently looking into what is possible there.
Definitely. Thank you. Great work.
Thank you. Well, thank you, Pascal, for a really interesting simulation. I look forward to seeing future results from that. So I'd like to call on our third presentation, our third paper, Visualise Cues for Enhanced Spatial Ability Training in VR. Is the author there?
Hello everyone, my name is Chen Qian. I will present our work on Visualize Cues for enhancing spatial ability training in virtual reality. Since it's difficult to sign up Zoom in China, I use my supervisor's Zoom account. For a better viewing experience, I will present with the pre-recorded video. Will present our work on visualized cues for enhancing spatial ability training in virtual reality. Growing research suggests that virtual reality is an ideal environment for spatial ability training, but the spatial tasks in virtual reality are complex. Learners usually cannot receive sufficient assistance to discover spatial reasoning rules in the training process. Exciting spatial ability virtual reality training systems make cues to assist mental rotation and visualization. It has been proved that adding view cues such as color or arouse to complex graphics or animation to direct attention is an effective way to improve learning. In this work, we propose 3 cues for learners to succeed in spatial tasks in a spatial ability training system called For Spatial. For Spatial provides 3-dimensional visualization, direct manipulation of virtual objects, and instant exercises with feedback. The tasks for learners are to observe and interact with the shape covered with several letters as patterns to determine whether it can be folded into the solid on the right. Next, I will introduce the 3 cues we propose. First, the color cue is a cue that different colors are employed to distinguish the faces with and without letters and the feet with different letters. When learners fold the shape into solid, they may not map the faces of the solid to the faces of the shape wheel, especially after the solid is rotated to a different degree. Color cues make learners more easily recognize the letters on which faces, discriminant edges, and the faces orientation. Second, the rotation path cue refers to a cue for visualizing the direction of the rotation. When the solid is rotated to the target direction, no spatial ability learners may be lost and cannot obtain an identical orientation as the target solid. Through this cue, learners can view the moving spatial wake and construct a rotation strategy in their minds. Finally, we propose a combination of circle cues and a detailed explanation to make the phenomenon and problem visible. The circle cue refers to a cue to highlight the differences between the target solid and the distracted one. This cue helps to emphasize the key points to solve the problem. In addition, it also shows a detailed explanation so that learners can succeed in their practice. The above are the 3 visualized cues we proposed to enhance spatial ability training in virtual reality. In our future work, we will investigate how cueing strategies in virtual reality impact mental visualization and rotation for K-12 students. These cues can be applied to STEAM education involving spatial tasks in virtual reality learning environments. Thank you for your listening. If you have any questions or suggestions, please contact Yunzhou.
Thank you, Yun, for your presentation. Are there any questions from the floor or in the other forums?
There aren't any in the other forums right now.
No. I was wondering, Yun, if you might elaborate on future work, how you might use this in a K-12 setting. In schools?
In our future work, first, we will test how these skills impact the improvement of learners' spatial ability and imagination, and enhance the acquisition of spatial reasoning skills. The cueing condition will be compared with the non-cue condition. Besides, learners will perform differently in immersive VR and less immersive VR. Thus, there would be a comparative study considering immersion as a factor. Thank you for question.
Thank you for the explanation. Are there any more questions for Yun? Oh, okay, well, we might move on to the last paper for this particular set, and that will be followed by a 10-minute break or maybe a slightly longer break, depending on how we go. So paper 4, collaborative learning with an augmented reality tornado simulator. Can I ask the presenter, please, to share their screen?
Can you see my screen?
Yes.
Yes.
Cool. So hi everyone, I'm Yemin Cho from UD, and I'm a PhD candidate now. And let me show my screen. So today I want to show about our latest work. It's called collaborative learning with AR tornado simulator. So it's a work that we conduct with a local school. So for motivation, so as we know, the global warming is a serious issue in the USA now. So from the NOAA's data, so it's about 16.2 from the past 5 years for extreme weather events. However, in last year, as you can see on the right-hand side, about 22 events happens very badly, cause about $1 billion loss in the USA. So that's why we want to use our AR to help educate our next generation to help the global warming can become slower, or how we can try to deal with the global warming. And from the NOAA, so NOAA is a standard in the States, how we gonna teach our next generation about the Earth science system. So Earth system, Earth and human activity, even climate condition and extreme weather. So for this work, we'll focus on the topic on extreme weathers. So several work has been conducted in the AR for Earth science. And as we know, I think all of us are AR VR experts, so we can really use the AR to tell abstract knowledge into to help students increase their motivation, their learning performance, and their special ability. And also with AR systems, we can just have the ability, we have shown the student about the study program, 3D animation, and even the spatial information. And also in this work, we help them to do the things by the interactive simulations. And so there are many work have been conducted with collaborative learning. And as we know, collaborative learning is an educational approach to teach and learning that involve a group of students and teachers to work together or think together to solve a problem, to design a thing, and even try to create new stuff. And AR has become a very effective tool to fast collaborative learning in physics, medicine, and even technical trainings. So in our work, so this is our approach. So we want to design and implement AR tornado simulator to help students learn by doing. So they can learn about the formation of tornado, knowledge of tornado, even different destruction part of tornadoes. By doing means they can work with their peers and even their teachers in the same time, no matter it's local or it's remotely. So they can build a tornado by choosing different parameters. Even they can also design a virtual township for them to do the simulations. So here's our app. So we try to come up by this kind of vision. So both of the students can standing in front of a big table, so they can use their iPad to run a simulation on the tables. So like we can use this kind of AR to teach the student about the formation of tornadoes, even their destruction power. So they can not only co-design a virtual Westward bridge just by on an iPad, they also can try to talk to each other to talk about, so hey, so what kind of a tornado we want to simulate to know about like the different kind of destruction powers. So I will show you a video about how this app works like in the real time. So here's a UI we designed for this simulator. So it's an iPad app. So we design in a form of iPad, so they can start an app, so they can key in like their gender and their age information. And also we provide like student kind of feature for them to learn about the AR. So they can watch a video from TED to talk about like what's tornado and why tornado will form. And they even can read documents in the app to learn more about tornado. And last but the most important one is like we provide tornado simulator for them to create a tornado. On the right hand side, you can see they are different parameters they can choose. So they can create a tornado with like different funnel width, different pitch difference, and different rotation speed. So they can just choose different parameters and talk to their peers, say, hey, what kind of like funnel width you want to create to visualize the tornadoes. And also we enable them to not only do a simulation, we only enable them to co-create the virtual town. So they can track like different house, different trees, different vehicles on a virtual ground, like they can later to do a simulation on. So here's like a snapshot of like what will happen. So like the tornado will show up in the middle of the township, and the tornado will just rotating like randomly across the township, and like with different kind of destruction power, they will have a different kind of destruction like for the house or for the vehicle. So here's a demo video I want to show about. So what would this app looks like? So they can get started app, then choose their gender and age. And after that, so they can create the tornado builder to try to do a simulation. So we provide two kind of form, single one and multi-user ones. And they can just put on the table to start simulations. And we provide the US guideline for the naive user who have never used AR before to guide them about how to really place the object on the tables. Yep, so the user are allowed to move like at different different angle to observe the tornado to see what happened to the house, to the ground, and even to the trees. So just skip through. So in the end, we will provide information about like what kind of the scale is like. They have 5 different scales called enhanced Fujita scales. So they will tell you about what kind of tornado would do a damage. Like for example, for this one is EF3. So EF3 will construct house will be destroyed and severe damage to a larger building. And so here's all its experiment design. So for our research hypothesis, so with our air tornado simulator, performance of the multi-user learning will be better than a single user learning one. So we try to do a comparison about does this multi-user learn better than a single one? Try to show like the collaborating really work on AR. And here's how we do the design to test our hypothesis. So we design a tornado knowledge test questionnaire. So we follow the Earth science curriculum from the USA, and we co-design this questionnaire with the science teacher to try to match what the students learn earlier in the class. So we use this questionnaire for pre-test and post-test to know like does the student really learn about from our tool, like our AI simulators. So for the study, so we recruit a whole class from our newer chapter in the intermediate school in the USA. So we work then to conduct studies in a class. So the procedure is so we divide the whole class into like 12 and 10 because we only have 22 students. So 12 students will learn individually compared to in a control group, and 10 students will learn in the pairs in an experimental group. So they are 2 different groups. So we do a pre-test before they use the AR simulators. So they will learn about formation and destruction power of tornado for 15 minutes. And after they learn by watching a video and by reading the documents, so we will ask them to start the app to do a digital entrainment for comprehensive AR test. So they can do simulations. So after a test, after they work with the iPad, So we will ask them to do a post questionnaire to learn about like what do they learn and try to get the efficiency of our app. So here's a result we find for our study. So they are control group and experiment group. So in the control group, the score for the students, they are 6.9 before they use the app. And we can find they are very similar score in the experiment group, so 6.7. So they are really about the same knowledge level about the tornado. But after experiment, you can find, so the control group is 8.9 for average score. But in the experiment group, it's 11.4, which means like, so they really learn better just compared to just in a score. And we also run an independent t-test to see does any really have a like significant difference from these two groups. We find out like the T is 3.682, which means they really show the significant difference with p-value less than 0.05. And so the conclusion, so the collaborative learning really can help students learn better in a group compare their individually. So then our next step, we try to adapt the free pedagogy to AI simulator to help the student learn actively, not learn like passively from the teachers. So that's all. Thank you. Any questions?
Thank you, Yanming. That was very interesting. Yeah. So Julian has a question.
Hi, nice simulation. So your experiment looked at if collaboration is helpful for them.
Yeah.
I am really curious to know if you have any sense of like, if you were to run, let's say, multiple people with the AR version of the simulation compared to multiple people with the VR version of the simulation. I'm really curious if you have thoughts of what you would find. Like I'm interested in kind of the value of AR that might be bringing to this, assuming that collaboration stays the same. If you have any thoughts on that, I'm curious.
Actually, I read a paper from Japan. They really do a study like this, try to compare AR and VR to do like a tornado, like streaming weather for the learning. The finding is like they are in the VR one, they feel more scared compared to the AR one, because AR one they just like look outside like a golf view. But for the VR one, they feel like they are really gonna be like went out by the tornadoes. But for my study, I just want to study about, so that's really collaborating really help for students to learn compared to like the single learning one. So that's beyond my scope of study, try to compare AR and VR to do the study for like a science, like, or especially like extreme weather conditions. Yeah, thank you for your question.
Thanks.
Could I ask Yanming, did you think about doing collecting any qualitative data?
I didn't collect like that because we didn't expect to interview the student, because we didn't do it on IRB as well, because we need to do the study in class. So like the teacher cannot give us so much time for we to do the study in her class.
Yes, that's common, isn't it?
Yeah,
That's
yeah,
common
because
with research in schools to get teachers on board. Yes.
yeah, we only cost like two whole class for us to do a study. It's a much they can give us.
Are there other questions? I think this would be a very powerful educational tool for the general public as well, in terms of educating them around, you know, the risks of natural disasters. And I'm thinking in Australia at the moment, we have quite severe floods, and people in the general public really don't have any sense of the severity of what can happen when there's a flood. And a lot of people drive through flood water actually, and many people die from that, or a number of people die each year. So having these types of simulation could be a very interesting public education tool.
Yeah,
yeah.
And although it's cheap, like in our corporate school, every student have an iPad to learn. So like there's no like more cost for them to acquire new tool like Arian just say like HoloLens is expensive, but iPad is comparatively cheap for us to conduct experiment or how we can build a tool for them to learn in AR.
And I note that Cole's just shared a Roblox game around disasters too, which I'll have to check out as well.
Yeah.
So any final questions for Yang Min or comments? No? Okay, we're running on time. How fantastic. What a group. So take note of your clock at the moment and we meet back in 10 minutes. So we'll see everybody in 10 minutes for the next set of presentations. And guess what? I'm the first one up. So yeah, I hope you come back. Okay, see everybody in 10 minutes. Welcome back. I think we're ready to resume the session. I'm up first, so thank you for listening. I'm going to present on a pilot project that we're conducting at the moment. We've conducted, but we're doing a larger scale study at the moment, which is really focused on students creating learning content for other students through VR. So I just need to make sure that I'm having a bit of trouble. Okay, I'm having trouble going through my slides, sorry. Of course, it's always the organiser who has trouble going through their slides.
On the display settings, you can likely just switch screens at the top.
We'll try that. Be a lot easier for me to see. Okay. So the study's part of the VR school study. This is a research that's been going on it's in its 6th year now, and it's about conducting research in school classrooms using virtual reality, both 3 degree of freedom and 6 degree of freedom VR. And this sort of research is relatively uncommon. There's been a recent systematic review on that. And most research that's conducted in schools using the technology really doesn't have teachers as co-researchers, and concentrates more on testing applications or experimental or quasi-experimental kind of testing of applications rather than student content creation. So currently I'm working with 4 schools in Adelaide, which is in a different state from me. I'm in New South Wales, looking at how we can use an easily accessible VR platform called Verdi, which doesn't need coding to create, for students to be able to create virtual learning resources for other students and other stakeholders. The pilot study that I'm reporting on today was conducted last year, and it focused on students, year 8 students, so they're 13 and 14-year-olds, creating a virtual reality learning resource for year 6 students or elementary school students. So they're 10 and 11-year-old. And the learning resource was on energy, so the science of energy. And students use this kind of what I would call no-code create platform, or a sandbox, to be able to do that. On the right of the screen, you can see there's a typology that I've developed, a pedagogical typology around notions of virtual reality environments and the degree to which learners are able to interact and have agency in those environments. I'm quite interested in this no-code create component because it's very accessible, and we give students tools, authoring tools, VR authoring tools, which are accessible. I'm very interested to see what they create in order to demonstrate different types of learning. So this particular study was really a first attempt to look at how students might create a virtual reality learning resource around energy for other students. So we had a year 8 class, a whole year 8 class, create a 360 scene. They developed the foundation 360 scene together with the teacher by going out into the playground and thinking about how energy might be represented in the playground. And then they took that away and either individually or in pairs embedded other types of media into the 360 scene to develop the learning resource for other students. And you can develop different types of media for these 360 scenes: sound files, video, text. You can see a text pop up at the bottom of the screen, and you can navigate around this. And you can and GIFs. You can also embed GIFs or animation into it. You develop on storyboard the scene on screen, but you can obviously interact with it through gaze-based navigation with a headset as well. So our year 8 students developed particular scenes for the year 6 students to teach them about energy. And most students were really interested in using this kind of virtual reality platform. It was really easily accessible for them. And they were much more interested in using this to tell a learning story, I suppose, than producing a PowerPoint. So there was some novelty effect, I suppose, to this particular project. What was interesting is that they didn't have many lessons, 6 lessons, 6 50-minute lessons to do this, and we actually ran out of time to complete the whole design cycle for the project, where they got to use the VR headsets to iterate on their design. But generally, they found it a really interesting project to do. And they're really excited in terms of producing something for other students. Girls generally did quite well at this task. So this is the second time I've found this in a study that I've conducted in schools. So girls generally did quite well in the task, particularly in terms of being creative in their development of their virtual learning resource for other students, but also in terms of demonstrating content mastery, science content mastery. The teacher, it's a mixed methodology. So the teacher actually recognised that students were quite interested in the project, that the topic of energy was a good topic because it wasn't too difficult from a science perspective for students to grasp and to be able to represent knowledge for that. And the Verdi platform, the 360 platform, was easy enough to use for students to be able to create and iterate on their design fairly quickly. And he recognised that many students had a sense of flow when they were doing this. So it was quite an interesting observation from the teacher. We chose one of the best Year 8 virtual environments to give to two classes of Year 6 students to see what they thought of that as part of this pilot study. The teacher chose that particular Year 6 virtual environment because we'd run out of time to be able to show the children all the virtual environments that were created. So we chose one. And the Year 8 students who developed the virtual environments also developed a pre and post content knowledge test. So they were involved in data collection with the Year 6 students. Now we found that there was no difference in content knowledge acquisition or learning gain for Year 6 students having viewed or experienced the Year 8 virtual world on energy. But the Year 6 students seem to have started from quite a high base level of knowledge about energy anyway, and that kind of had implications for us in terms of being able to work with the Year 6 teachers around having students develop these kind of tools to measure knowledge gain so that they were a bit more targeted in terms of our level of knowledge. We also asked the Year 6 students to give us some feedback on using a system usability scale, because we wanted to make sure that it was easy, if we were going to proceed down this path with the study, that it would be easy for students to be able to use the Verdi headset and the Verdi software to view the learning environments that other students had created. And most found they had quite a good experience of that. Our students generally thought the VR headset, looking at the VR environment, using the VR learning resource was cool and wonderful. Minority of learners, however, did experience physical kind of reactions to being in VR. So, and this is mobile VR, so there's very little interaction in it really, but it was interesting that we got these comments. So what did we learn? Well, we ran out of time for the project, so we know during this next phase of the project, we're using this approach for students creating learning resources for other students in more integrated units of work, so units of work that cut across subject areas so that we get more time to use the VR in class and the Verdi platform in class. We found that, and this is often the case, that there's kind of a lag or some issues around technical setup within schools. And even though we say to schools, you need to get onto this early to make sure that the platform works and that the phones can, the access to the Verdi platform can go through your network, often this doesn't get done because schools are very busy until the last moment. So we're on to this technical setup issue earlier, I suppose. We found that using kind of VR as a new type of media was both engaging and interesting for students, and it certainly was quite good for girls. Girls were very interested in the creative as well as the content knowledge or kind of acquisition for this, and it was a really nice kind of media, I suppose, for students to be able to demonstrate creativity as well as scientific communication. So the next phase of our project, we're working with the 4 schools. We're working across 4 different subject areas, but each with a focus on content creation, students creating learning resources for other students and other stakeholders. We're well into that at the moment, and we're using a similar set of instruments across sites to get a kind of holistic picture of learning, both for the content creators, but also for those people that experience the learning, or the students that experience the learning resources. So you can follow our journey at brschoolresearch.com, where we blog about it regularly. So thank you. Are there any questions?
If I may, I have a question for you, Erica.
Certainly.
Yes, and thank you for your speech. I think that the no-code authoring tools are a hot topic that needs to be addressed by our community to level up the game of building this experience to the people. And I was wondering, you partially answered to that in your summary, but I want to ask you for an insight about these tools. If you think that these no-code tools should be better to be, let's say, designed as non-immersive or immersive. So these tools that we want to give, let's say, a PowerPoint solution for the people, is better that we focus on desktop editors or on immersive editors?
Yep, and that's a great question. For children and young people, they need to have access to both, because there'll be a percentage of children and young people that will not like being in VR. And so we need to be able to have both types of editors and both access to creation through screen-based as well as immersive platforms. And that way you're including all students, not excluding students who don't like the virtual experience. So I've been conducting research for 6 years, and there will always be a minority of students in class. It might be between 5 and 10% of students who don't like the VR experience. And so for them to be able to engage in the same learning and the learning task, they need to have access to both. And I've conducted kind of quasi-experimental research in this area where we've compared not VR to non-VR, but now I'm much more interested in, I suppose, really thinking about giving the power over to students to empower them, and these kind of accessible sandbox applications in both screen-based and immersive modes are, I think, a big part of the future of education.
Thank you for your insights.
And I think I've run out of time, but thank you for the question. And any other questions, I could talk about this till the cows come home. So the next paper 6 is
I will stay here for the
bot undercover.
Yeah.
So we'll get bot undercover on the use of conversational agents to simulate teacher-student interactions in remote learning. Thank you.
We share the screen. You see my slide? I think.
Yes, we can see it.
Yeah.
I think we are in the. Okay, sorry. So, my name is Gabriele Prattico. I'm a PhD candidate at Politecnico di Torino in Italy, and today I'll present this work about the use of conversational agent to foster interaction in remote learning scenarios. I think all of you are familiar with remote learning, especially in the synchronous form, which is easier to deploy in respect to the asynchronous one that requires a lot of material to be prepared and so on. And so especially for institutions and individuals that let's say use remote learning as a temporary transition and fallback solution, as has been done in the last 2 years all over the world. The synchronous one is the most diffuse approach, also because it's more similar to the traditional classroom, so also easier for teacher themselves. And also there are plenty of tools and platforms as the one we are using now that allows and enables this kind of remote learning, and also social VR platform as well. For sure, these tools provides teachers with fancy stuff that maybe were not allowed to use in the classroom, but anyhow, they present still some limitation, especially on the social and emotional aspect of teaching. So one of the most reported issue of these synchronous remote learning is that students appear to be less willing to interact with the teacher, even if solicited to do so in such scenarios. And it is indeed not so uncommon to experience a situation in which the teacher opens the stage for question and nobody answers. So contributing to fuel an unpleasant and awkward silence. So this induces bashfulness is indeed exacerbated by the higher social pressure that might be experienced in this context. And countermeasures are not often effective. So to mitigate this issue, we propose to stimulate the interaction between the actors involved in a classroom in remote learning, VR in particularly, by exploiting an undercover conversational agent that is acting as a participating student. So the core idea behind is that this conversational agent could relieve the social pressure by icebreaking the interaction between teacher and students, making the students aware of what happened when a teacher answers one of their questions, so that this is a safe place to ask questions, and eventually allowing them to feel more confident in asking questions themselves. So in short, the CA should provide a reference behavior to be taken as an example by real students in terms of code of conduct, and in the end acting as an interaction catalyst. So we performed an experimental evaluation by proving this concept. We leveraged Mozilla Labs. Actually, we implemented a custom version of Mozilla Labs, which we ran the teacher, which is this green avatar controlled in our experiment by a real professor that followed a scripted lecture. And then there is a real student connected to the platform via the MetaQuest 2. And also there are, as you can see, many avatars. These are actually dummy students, so there are just avatars but not controlled by anyone, just to raise the level of social pressure. And there is one of them that is actually controlled by our conversational agent. It was implemented through the Mozilla platform and using dialog flow, and it was allowed to both hear, so interact by hearing and speaking to the classroom. We devised and allowed the agent to support 4 interaction patterns, and of course these arise from the teacher and students, so not just the agent itself. So the first pattern is the student asking for clarification, the teacher that may raise a question to the classroom. It can be also the rerouted question from another student, the student that can answer this question, and the fourth case is the monologue of the teacher that also include eventually the student clarification answer. So we devised a preliminary study with 16 volunteers, split into groups for between subject design. The first group experienced the setup as I just explained with the active conversational agent. And in the other group, we turn off the agent and replacing it with an additional dummy student. And it is worth noting that all the participants were told that all the other avatars were controlled by a real human, including the CA in that case. We collected both objective metrics and subjective metrics for investigating the learning gains, of course, the interaction analytics, so the level of interaction with the real student, and also about the perceived aspect of the the learning experience, so about the engagement, behavioral, and the social presence aspect with the teacher, the social pressure, and so on. So to outline the key results, we found that in the group with the CA, it was experienced a more enjoyable lecture, and participants were more prone to ask for clarification, and they experienced a lower social pressure. The CA also aided in lead to a better understanding of a teacher explanation that led to a perceived better learning performance. However, we didn't find any proof by analyzing the objective metrics, so it was just a perception from the participant. Not we didn't find any significant differences in the quiz marks. Also, about the social presence between the teacher and the real student, we didn't find an effect on the by the CA, so nor detrimental nor improving. So it's good that it does not have a bad impact on that aspect. And also the CA was perceived overall as an intelligent, friendly peer, which is important. We were afraid that it could be perceived as in code with the teacher, which was not the case, as not distracting, and also perceived as controlled by a real human. So to sum up, the CA was able to relieve social pressure and stimulate this student-teacher interaction. Overall led to a more engaging and satisfactory learning experience, and also we didn't find, for that case, objective improvement, but the perceived learning performance was increased by the presence of the CA. For the future, we want to study what happens when we deploy more conversational agent, and also varying the ratio among the conversational agent, dummy, and real student, and also allow the teacher to feed the CA in real time on demand. So for instance, instead of asking a question to the classroom, to use the CA to raise that question for him or her. This concludes my speech. If you have any question, I'm willing to answer.
Are there any questions? Gabrielle, I'm quite interested in the issue about being in cahoots with the teacher. Would you mind explaining why you were concerned about that? Like that's quite interesting from a pedagogical perspective.
Yeah, we were afraid of that since, of course, I just skip a bit of details, but the level of interactivity in which we tuned the CA to intervene was a good balance between having, let's say, too much participative student that, and in some cases that could be perceived or too participative, or also as in code if the let's say the answer or the question were too much, let's say, good for the previous knowledge expected from a peer. So it is a matter of finding also a good balance on which kind of question is are good to be asked for the CA, and also the kind of answer that could be given. So in the design phase, we also collected the real student behavior before going for the building the intelligence and of the CA for that reason. So was particularly relevant for our use case. Hope this answer your question.
Yeah, thank you. There is one question in the chat, I think. Okay. So can you see that? And then after that question, we'll need to go to the next presentation.
Yeah, we actually, the topic was, we decided to go for a very simple lecture on the solar system to be able to feed in many details, so to have a more sensitive quiz for learning performance. And so we made a pre-post quiz, of course, to assess, since it's a very simple topic, we want to have a higher sensitivity on that, and also allow a whole range of people to participate in the study. We go for 16 years old to 52, so to have a wide spectrum.
Thank you.
Thank you for the question. I hope it...
I know there's more questions, but we may need to just wait till the general discussion.
Yeah, the CA, just quickly reply, was not a Wizard of Oz. It was actually controlled by a logic, but this logic worked well for the scripted lecture. So it's not a full Wizard of Oz controlled by one of us, but it was a proof of concept for AI for that particularly scripted lecture.
Thank you. Thank you so much. We look forward to discussing that more. So I'm calling on, I think Vidya's up next for exploring factors associated with retention in computer science using virtual reality.
Yeah. Hello, everybody. Let me share my screen. Oh. Sorry about that. So can you all see my screen?
Yep.
Yes, we can.
Fantastic. So my name is Vidya Gaddy. I am a PhD student in the computer science department at Colorado State University. I work underneath Francisco Ortega, and he supported this project while I was doing my master's. And yeah, let me just jump right into it. I'm sorry, I think I muted myself. So the inspiration to this work was the clear gap in graduation rates between your standard Caucasian males and females even, with these underrepresented minorities in this field. Diversity is going to be key to technological fields in the future. So it felt really imperative to figure out the reasons behind this retention gap and enrollment gap that we see. Lots of research has shown that belonging is something that underrepresented minorities really don't feel in the computer science community. So in an effort to understand this concept of belonging better, we sort of parsed the various elements of it apart. They're also all obviously intertwined, but these are some key factors associated with belonging, at least as have been identified by underrepresented minorities. So that would be self-efficacy, how somebody feels about their own ability, goal orientation, something that's really been highlighted in recent years as a major factor in a person's decision to continue in computer science. And then there's their family background, what sort of experiences they grew up with, like role models, that sort of thing. And then there's also demographic characteristics, whether they're going to feel like the people around them are their peers. And so in order to do this, so the reason why we wanted to do this was so that why we parsed these factors out specifically was because we wanted to inform future initiatives to determine whether or not any of these factors are more significant than others, especially in a computer science context, to improve retention and involvement in computer science. So as a brief overview, I'll go into more detail in the next slides. The experimental design we used, it ended up being repeated measures so that we could garner more data from fewer participants. As you'll see later on, our primary reasoning to do this experiment ended up being a major limitation in that we weren't able to obtain the desired experimental group due to COVID and all sorts of restrictions, as well as the fact that underrepresented minorities are simply a minority in a computer science department. So that's the primary reason we used a repeated measures design. Then we had participants wear a virtual reality headset and interact in a simulation as an avatar, listening to audio cues, specifically voicemail messages that each highlighted one of the 4 primary factors that I discussed earlier. And then we had them fill out surveys as they went to determine their desire after listening to the audio cue. So we chose to use virtual reality in this experiment because in psychology, there's just a myriad of issues when you're doing surveying among people, especially when it's kind of an easy question to simply answer the correct way rather than the way that you actually feel about a situation. So in this experiment, we allowed people to embody an avatar, and we gave them a character that was not themselves, but a first-year student in college who hasn't decided on a major, but basically has a general appearance that is similar to the participants. So this kind of gives the participant the opportunity to separate themselves from the question being asked, while also maintaining a certain personable reality within the simulation. Yeah, and then we also gave them obviously all of these choices to make them feel more at home in the avatar. This was done because of our pilot study showing us that it was something that participants really appreciated. And then our questionnaire that we had at the end of the study, and I guess interweaved with the simulation, it was in a simple Likert scale design. There was a baseline measure, so we had participants just answer this question: how likely are you to agree to enroll in a computer science course in general? And most participants in this first question, and then after being within the simulation, their answers changed pretty drastically. So it seems like there was an impact from being in the simulation and listening to these audio cues. We also, so the paragraph that I have here is kind of an example of one of the 4 audio cues used for each participant. I highlighted the part that changed between each condition. So this is the condition on goal orientation. With a background in computer science, you will have many opportunities to contribute new technologies and innovations to your community and the world. If your goal is to help others, computer science may be right for you. Would you like to enroll in this computer science course? And then participants had the opportunity to answer this question. And then there's also an audio cue directed towards their families. There's an audio cue directed towards their self-efficacy, so their ability as a person. And then there's their demographic characteristics also being highlighted in another cue. And we analyzed these results. We had 24 participants and 96 data points to review. in this experiment, I wanted to look at the preference within each condition to determine if the participants seem to favor one answer or another within each condition. And then I also looked at the preference between conditions to determine if there's one condition that was more favored than the others for future initiatives, like I said earlier. And what we found was that within conditions, self-efficacy was pretty evenly distributed. So it had a generally positive skew, but too many participants had a neutral reaction or somewhat positive reaction rather than an extremely positive reaction. And then family background, it had a largely neutral reaction. So students didn't seem to really be affected too much by the audio cue highlighting their family. I think that in the free-form feedback that we got in the survey, participants didn't seem to appreciate the invasion of privacy in this audio cue. So they didn't dislike it enough to say that they wouldn't take the class, but they didn't respond really positively. The response was neutral. Then the goal orientation had the most positive reception, and the demographic characteristics cue had the most negative reaction, pretty significantly negative reaction. And then between conditions, so looking at the mean values for each condition and comparing those with each other, we see that self-efficacy was had a much more positive response from people than family background or demographic characteristics, and goal orientation had the same much more positive reaction than demographic characteristics or family background. And there wasn't a significant difference between demographic characteristics and family background, and there wasn't a significant difference between self-efficacy and goal orientation. So in conclusion, I think that in general, along with the free-form responses that we got from participants, goal orientation seemed to be something that they responded really positively to. They didn't feel that it was invasive at all. And so in the future, like if an administrator is trying to convince a student to enroll in a course, I think that goal orientation is likely going to be a more powerful tool to use rather than speaking to their demographics or family. I think that it's also important to note that demographics was specifically disliked. It wasn't neutral, it was disliked. People chose not to enroll in a course if they were told that their gender and ethnicity were in consideration for this role. And obviously there may be the effect that I was talking about earlier, where people don't want to believe that this is something that affects them, but it might be something that is affecting them in practice, like we see in nature. And then there's also the
get you to wind up. I'll just get you to wind up because we'll have one question only, and then we have to get on to the next one.
Yeah. So like I talked about earlier, we didn't get a lot of diversity in the study. So in the future, that's what we would really like to focus on, is actually garnering the responses from highly diverse groups so that we can actually get a sense of what our target group is interested in rather than the general population at our university. So yes, thank you so much. Any questions?
Fantastic. Yes, we have a question here from Jerry. Can you see it in the chat? And from Julian. So you've got 1 minute to answer these questions, but we can come back to them in the general discussion, but would you like to take one of the questions, would you?
Sure.
Overlap.
So I think that we did have a desktop version. So, but the responses were not significantly different between those two parties. And there's also only a limited selection of participants who actually did the desktop version. So we couldn't find statistical observations to look at the difference, but that would definitely be also something we'd be interested in future work.
Thank you so much. Such an important topic. And I really thank you for doing this research. But we'll come back to the key issue around diversity in the general discussion. So now for our final presentation, which is on Teach in VR, a virtual reality classroom for remote education. Very timely indeed. So Florian?
Let's see. Are you seeing my screen? All good?
Indeed we are. Yes.
Excellent. Okay, so hi everyone, and welcome to Teach in VR, and hello from Germany. I think the name pretty much gives it away. It's a virtual reality classroom for remote education, and I'll first give you a rather broad idea of what we're even talking about. So it's a VR classroom for both remote and co-located teaching. It supports a range of teaching activities from presentations to guided tours, private study, and it focuses on the rapid creation of classes through reuse of existing teaching materials and teaching know-how. We're also trying to lower the barriers of entry here, especially for, as you may know, very time-constrained teachers. From a scientific point of view, this is for us now a sandbox environment where we can explore teaching concepts that are well supported by or even unique to VR. And we also want to explore how these spatial, so we're giving information spatial properties, and we want to explore how these spatial representation may excite mnemonic mechanisms at work, and thus may aid the learning, the understanding, and prove VR to be a powerful tool. Of course, we also want to find or shed light on parts where VR is the wrong tool to use, and encourage also finding like misuse. And I hope in the course of this presentation to fill this empty room here for you with an idea, media of what this tool is. Our key cornerstones are basically that we want to have a platform for systematic exploration and evaluation of educational pedagogical methods in VR. We want to have full control over the variables so we can do a proper scientific analysis of the effects of different variations. With COVID especially, but also for remote students for various personal reasons who might want to or only be able to join lectures and classes and study programs remotely. We want to make sure that we be able to reproduce interactions naturally, and not just as in Zoom where I'm looking at a screen and I have no way to address any of you because I'm not looking at a certain person. You cannot tell who I may addressing just more naturally. So we want to incorporate these. We also want to evaluate, we also want to address privacy concerns, especially in Germany. It's pretty strict for schools, especially for underage people. And yeah, thus we want to stress this point. We did not implement it in UBeak, which you might have heard in the course of this workshop, in this conference weekend day. But I would advise taking their tutorials. Unfortunately, it's already over. It was just this morning in New Zealand time, at least. Last but not least, we also want to evaluate the improvement of learning outcome by, for example, leveraging this spatiality that comes inherently with VR. We asked us a number of questions. Some of them were like, which kinds of novel teaching formats are only possible in VR and which ones are well supported for VR? And how can we actually make it more usable for teachers through reuse of existing know-how and material? At first, of course, we looked out there what's existing already, and we took a group of students over the course of a semester to evaluate different existing platforms. And at the time, Spatial IO was what stood out most for us. This is a year ago, and many features they have today were not in there back then. So we wanted to be able to dynamically add features we envisioned, and we want to match privacy concerns. And we had a number of reasons why we, in the end, decided to, hey, let's still build it ourselves and have this like platform that we can use. I want to stress the differentiation to bespoke tools, so tools that explicitly teach one scenario. They are incredibly powerful and incredibly helpful, as we've seen also some in this very workshop, but they have long development times for each scenario, as the developers may be able to tell you, and they're less configurable by the teacher. So we want to provide instead a universal platform, not as an replacement or alternative, but as an extension to these bespoke scenarios, where we can teach a variety of classes. So Teach in VR tries to stress this ease of use to let users focus on user-to-user communication rather than user-to-system struggle. And we try to avoid complicated input, hidden menus, all these things. We also want to focus, so this is basically the user end, the time constraint of teacher. We try to automate the import of files and everything to just keep it simple and stress that hey, here's a tool, just use it. You don't need to know 3D software development. You don't need to know anything. Just plug in your files, go ahead. And thus we want to support this rapid development of classes with familiar teaching methods they know. For this, we use the Oculus or Meta Quest with incredible hand tracking, and also for affordability. We have a dozen of those. We can use them in classes, and they're just more affordable than high power wired HMDs. And I'd like to turn this off in this application can be a guided journey, a physical journey through a path, through a room. And we had one preliminary study, and I'll show you some images now, where we have just one of probably many possible ways of organizing content in here. In this lecture, we organize content 360 degree around the students. The images here are just mock-ups and not the real presentation that we had. But we arranged the content 360 degrees around the students, and essentially just had the teacher guide the students through the room, mostly leveraging also the unique spatial associations or spatial features, characteristics of the room to stress the spatiality point that we wanted to revise or examine. And afterwards, we have this large patio outside where we can meet and discuss in groups or separate group works, where we not like breakout rooms where we have no way of viewing what the others are doing. The teacher can still supervise everyone. We have this video where I'm not sure how I'm running for time, especially. So anyway, yeah, again, we're targeting the Oculus Quest with hand tracking. We have this large space. We can easily replace this 3D model. Of course, the software works anywhere. This is just a approach to possible interpretations. On the right-hand side, you see what the user sees. In the middle, you see how users are now joining and starting to interact with content. And are, in this case, just 2 users because we needed to mock it up because we wanted to use neutral content. So we have videos synced reliably across all connected clients. Everything, volume, etc. is just synced reliably, so the users don't have to care about it at all. Less typical for standard teaching material of teachers are 3D models, but we do support them, of course, in these applications. It's just a no-brainer to import them as well, encourage teachers to use it. But of course, also typical slides, mostly images, are very, very easy to import, very easy to use, very easy to just guide the users through experience, save points, and configurations. Of course, we also have this hand sanitizer. Oh, it's gone. It's COVID times, so we needed to have that in there. And then we have outside space for just group work. Again, trying to get an overview for the teacher and not lose their students in whatever they may be doing. That's the short demo. I have a short, let's see, PowerPoint 1 to 2. There we go. A few galleries, pictures just of more impressions. Again, these are just spatial features of the space to have users have detail that they can associate information with afterwards. In this short, primarily preliminary study we ran, we compared it against video chat lectures, and overall it was pretty positive feedback with increased sense of co-presence. These are just a selection of quotes taken from the survey. And yeah, in summary, we can say that for teachers, for teachers and students, we try to stress this point of higher sense of co-present, persistent spaces that they can revisit after lectures. And for our research purposes, where we are able now to implement any feature we can think of very easily into this platform we've built. and help understand in which situations VR may be useful and where it may not be useful. So future steps for us now, or actually what's already doing now, what we're already doing now, is collaboration with other chairs in schools to actually bring this to users, get their feedback, quickly implement whatever they address. We're planning a series of trials with real classes in schools, and also prepare thus a long-term study. And as a feature for future work, I have a sneak preview here, because with all the, in the light of this loosening, sort of hopefully continuing to loosening COVID restrictions, it's exciting for us that we can now do it all hybridly. So we have this large space at our campus, which I use for an example here, and we have our application now being able to align itself, the virtual world and the real world, and have users connect each other, and now being able to have it for both co-located on-site users and remote students. With that, I hope you have now a good impression of how teaching VR looks, and I encourage you to press that unmute button and ask some questions for discussion.
You did really well, Florian, given how early in the morning it is there.
It is 4 a.m. Yeah.
Are there any questions for Florian on this very interesting kind of social VR space? Yeah. I'm very interested in that you flag privacy implications, like who owns the data, because obviously you can collect lots of very personal data, particularly if you've got kind of biometrics folded into the space. So how are you approaching that? I'm very interested in that.
So we're of course trusting the hardware manufacturer also to not grab the data on the way. So we are bound to use the Oculus Quest currently because it's just affordable, it's usable, we can scale it, it has high fidelity, and we can just implement many social cues that we encourage or find it very important. Thus we rely on them not grabbing those information from us. Apart from that, we have an on-site self-hosted instance for networking, and thus we basically are sure to not transmit basically any data to any other server other than ours. I think that's our approach, our takeaway.
Thank you. There's a couple of questions in the chat. Warren, would you like to take those? So you've got a couple of minutes to answer those, then we're going to move into the general discussion.
Okay. Let's see. There's so much research. Yeah. So social VR, especially for school purposes, I think privacy is just key, and underage students especially. If the teachers decide for them to use this platform, that's always tricky. How have you dealt with something like the need of screen sharing? So there are different, it's very difficult because you now have this, I'll show you real quick, that is not possible anymore. Usually for us, we ran our test in COVID times, so we were all in different locations. We had a brief first initial, like, this is how it works with just screen sharing via different tools where we can screen share through the Oculus Quest. So there's a tool called Screen Copy, or just Oculus Developer Hub has a screen sharing method. So we use this, but it's very, very tricky. The open source release is, I think, pending. It was started as a research project. We're now like continuing to gather collaborations at our campus and in the region with schools. I am not the only decision maker here, so I'm not sure if or at what point maybe this will come to open source. And in class, yes, we would really like to see, and we will try it in our smaller courses that we have, to do it both in classes and not just remote, but on-site in classes use. This is this approach with hybrid fidelity here, where we have, there we go, where we have this ability now to have a crude model of the space and then use the features that the devices allow us today to use to have both. And this is actually possible in this application already to connect remote users and on-site users alike, having the remote users being visualized by an avatar and the on-site users mostly by either video pass-through that the Quest can handle very well, or also avatars, whatever they choose to be represented as. I don't know if that answers Gabrielle's question.
Thanks, Florian. It's a really interesting virtual space, isn't it? I can't wait to have it try. Sure,
Yeah.
one day, jump in and have a try. So thank you very much for your presentation.
Absolutely.
So we now come to the last half an hour where we're opening the floor for just general discussion, I suppose, and feedback, and possibly covering questions that weren't answered before as well. There is no agenda for this or, a set of questions we'd like to answer, but I know there's been some of us who've been coming to this workshop for quite a long time now, and you can really see the kind of progress in the field, I suppose, and kind of the interesting questions that are arising as the tech progresses, but also as our pedagogical understanding progresses. So would anyone like to kick us off with some general observations or back to a question they'd like to discuss?
Actually, I have a question for Professor Julian Radu. I was particularly interested in the aspect of the AR as detrimental, or any case, the let's say, adding some information somehow in the process could be detrimental to the learning performance. And I was wondering if maybe this is not some stuff that is strictly related to the AR itself, but it's more like that by providing such information, we are suppressing some step in the cognitive process. So, for instance, in that kind of instruction of a lecture, people will build a mental map of for them is the flow, the visualization, the magnetic field, and so on. So maybe you feel is more that the AR visualization actually, let's say, replace the cognitive process in a way that hinders ultimately the grasping of the knowledge, or is something more intricate that happens behind the curtain?
Yeah, I think can you hear me okay? You can, right?
Yep.
Yeah. I do feel like in the AR condition, when there's like so many visualizations, the attention of the learner sort of gravitates onto those visualizations, especially if they're these kind of new and they look virtual. So people's attention focuses on the things that you're showing them with AR. And I think that kind of hides other things. So they are paying attention to the magnetic fields because they've never seen those before. But at the same time, they have less time or less cognitive resources to be thinking about like, how does it feel when I put my hand on it or something like that. So I think there's the fact that they're visual. It's kind of their visual processing. It's also attention. It's kind of like taking over their attention. And I think there's also something about, it's interesting to think about when to show them and when not to show them. Because sometimes you might want to show them the magnetic field and then take it away so that they think about other things. Or maybe you don't show the AR at the beginning and then you show it after maybe 5 minutes or something. So yeah, I think there's like multiple
extraneous cognitive load, or is more about the let's say previous skills with the AR. So let's say if a skilled user could behave differently, skilled in AR, not in the subject. I mean.
Mm-hmm. Yeah, that's possible. There's definitely possible too, of how much are they excited about, wow, I've never seen this before, let me look at every little thing. Or if somebody who's very familiar with it and they're like, okay, what's the important thing in this visualization? Yes, I definitely feel like the background of the people who are experiencing these is very important. And we notice there's a time period, even with this application, when people put it on, it takes a little bit, if they haven't seen this before, it takes them a little bit of time to kind of understand how the AR works, and the fact that, when they move, the visualizations stay locked in the world. And that process is also, I think it's important to budget for that, to let people become comfortable with the experience before you actually show them and evaluate their learning. So yeah, it definitely touches on that. Thanks for raising those. I feel like
I
there's so many
will
factors here.
continue, but I will leave the space to someone else. I will.
I'm curious if anybody has done any longitudinal studies. I feel like that last point of this is the first time I've ever used VR, and right, really gets in the way of us really understanding how people are learning with VR or AR. It's so hard to really say that, oh, that 15-minute training we gave them is getting them over that hump. I really haven't, it's typical studies still.
I think longitudinal research would be really important, and to actually, follow through the same, to have quite a sophisticated sampling framework for that, so that we can follow different groups of learners through the learning process over time, with particular variations of virtual environments and kind of interactive platforms. And there's a lot going on. Do you know what I mean? I think Julian's alluded to this. So it's really around both diversity of the groups, different exposure to technology, confidence and efficacy with technology as well, and then being able to follow them through over time. So the sampling framework would have to be really well thought through, Kyle, I think, because you'd really want to pick up differences in groups of learners, as well as what you're exposing them to and why, and the purpose of the learning. So a lot of the time we measure content acquisition as learning, but that's not the only type of thing you do when you learn. Like learning's much bigger and broader and more interesting than that, as we all know, because we're great. Everyone here is a good learner. And it's fairly reasonably effortless for us, but for other people it's not. So yeah, no, I agree. And longitudinal research is expensive as well, isn't it? So it's getting funding for that sort of project. But like, I agree with you, it would be amazing.
I wonder if systems like what Florian presented on are a pathway towards something like that, right? If you can actually teach a full course in VR the whole time. And I know people have done that, but maybe not with immersive VR, because it's still very hard to get into the hands of students, or a significant percentage of them.
Again, yeah, we're trying to do this. We're trying to schedule this long-term or plan this long-term study, but there's just a difficulty of getting students, because you're also putting not them at risk, but they're the lab person who has to. I mean, some of them also have to have bad experience for others to have significant better experiences, and it's just difficult to also have schools. I mean, we're talking about schools who start to implement tablets. VR is just another step, which is why we've initially started with using just students of our classes, which we can just expose to it and just reach out, especially in COVID times. We just pass out Oculus Quests to them and started teaching VR in VR and trying to find what works and what doesn't work. But this is not a systematic study. This is our initial ground covering, and then now we're hoping to find enough different labs also to cover this diversity of, again, students, learning types. It's difficult.
I think it's also, so as these devices become more and more popular, it's going to become easier and easier to do this, right? Because people are familiar with it and there's lots of them available in schools. So I'm hopeful that in the future we'll be able to do this. There might be some interesting effects though. So in the past, this actually reminded me of a study that I did on children using augmented reality. And it turns out that the children who had more previous mobile phone experience actually did worse on the augmented reality than the people who were brand new to it. Because the people, and this is just kind of an example to show you that people who are new to it might actually respond kind of better to it than the other ones. And the reason for this is because with these kids, the people who are new to it, they were super careful when dealing with a mobile phone, because they were like, wow, what is this? It's very fragile, so on. And the people who had, so the children who had more experience with mobile phones, when I asked them to do augmented reality, they would hold it like this and try to start playing. But by holding it like this, they're covering up the camera. And so this behavior that they were so used to it actually got in the way of their, being able to do this new thing. So there might be some interesting things we find once we start doing these.
I do share the same experience, but with VR also. So we somehow I found that elder people, so 70 years old or more, are let's say try to instinctively find the controllers mapping better than 50 years old people than 70 years old. So there should be, so for AR you find it's for the children, for the elder one. For VR maybe there is a connection. I don't know. But it's
sorry, go on.
I was going to say that one of the really hard things going forward is going to be that we with longitudinal is that we need to develop content, right? But we kind of always start with the thing it's going to work best. Because it's our best idea. It's sort of like, I'm going to do the magnetic field visualization because that's already 3D and that's going to be great. But what are the other physics that you're going to be able to put in AR, and are you going to be able to use AR for that effectively, as Julian pointed out, right? It's not everything is great for AR. So I think we might struggle to really test the sort of like longitudinal type things if we don't really bring in some of the traditional content into these experiences and really like knit it together very nicely over the long term.
Maybe it's not fully, let's say, the way. I mean, maybe we should go for not doing in VR or AR what can be done in classroom, but just complement as a. So maybe this is another, let's say, open point. So just to find new ways. Florian talked about that, but in the end didn't develop the concept during the presentation. I was trying for that, but yeah, I'm also interested in finding ways of different pedagogical models that can be done just in VR and in this kind of media instead of other stuff. Could be the complementary way to fully exploit these technologies. Just my outlook on that.
So there's a tension between ordinary institutions and schools investing in equipment and wanting some evidence that this technology is good for certain types of learning over others. And so a lot of the previous research is really focused on why would you use VR or AR rather than another type of traditional pedagogical approach or media, or where I think we need to let some of that go in some ways and be much more exploratory and playful with the technology. This is why quite like the idea of, well, I mean, I can't say learning in VR might be better for X, Y, and Z than this, but hey, here's a new type of media. Let's use it so students feel empowered to create with an authentic pedagogical framework, I suppose, in mind. In some ways, we're tied to this kind of trying to prove that it's better than a different approach, and I think that kind of mindset might be, I don't know, holding us back a bit. But that's just me as an educator, I suppose. Of course, that's the scientific approach, isn't it? And the love of experimental research. But I do, in some ways, and that's perfect for getting funding. But it might not be the only good path forward. Yeah.
Well, actually, there are situations in which the institutions are more willing to invest in VR than in traditional classroom. It's the case in which let's say we have many students for practical stuff, and you might need to build, let's say, or acquire some equipment that is more costly than the VR, then you can retarget. So maybe technical universities are also technical schools are more interested in that. So, but it's a really specific use case of simulation-based VR scenario. But the mixed approach, as Julian written down in the chat, I think we should maybe go towards that. Maybe explore a bit more what can be companion to the standard classroom.
But I wonder if there's something interesting here about, we might have multiple things that can teach a certain topic really well, right? And so it might be VR is good for teaching this, but also, I don't know, drawing activities that get people to think about narrative or things like that. Like that might also be useful. So I'm not sure. I guess we're thinking of this from a reductionist kind of perspective of like, we need to find the optimal technology. But I wonder if, the answer is that multiple things can work.
I think there is the optimal technology, and we all know what it is. It's good mixed reality glasses, right? That can put whatever we want in a space where we want it. We're just kind of waiting for it, right? So it's not necessarily the technology that is going to be the problem maybe in the future, but it is choosing, should it be a 3D graphic? Where should we put the 3D? When should we have it, disappear and focus on the physical, right? So we're kind of already exploring those things, but I think we do a bad job, I myself included, of like saying VR and like lumping that with headset, right? And that's not necessarily the case. We all know that, but we have to do a better job in speaking to the public about it.
Good point.
Other people who would like to have to dive in here, who haven't had a say?
Another major concern we always face with reaching out to teachers is also this concern of, so especially because we're mostly working on the VR headsets currently, it's always this concern of health and safety. I don't know if you guys experience that too, but probably the phones are a good way around it also. Yeah.
So
You mean physical?
Yeah. Go on.
I was just wondering if you meant like physical safety or, social, like emotional safety.
I guess both. I meant, or in my head was the physical, be that eye strain or in VR running into things, which is why we started aligning real and physical worlds. But yeah, especially for kids in development. Yeah.
And there's only a couple of studies that have been conducted with children using immersive VR or VR with headsets. You know what I mean? So it's really under-researched area. There's just, so there's a lot of, there's two camps, let it rip, let everyone have a go, it'll be fine, which is the PlayStation camp, really. Where lots of kids have got PlayStation VR, PlayStation VR and off they go. And then there's the other camp, which is a bit more, well, it's a minority of children. Generally, the little research that's been done, there are a minority of children who are adversely affected. Like they have balance issues or, there's some, and then there's a little bit of research on false memories being implanted in younger children through highly immersive experiences. So there's a little tiny bit of research on that, but it's a really under-researched area. And just even thinking about a classroom, how you would use this in an industrial age classroom, where you need play areas to make it really safe, properly set up play areas. It is just, what do you do? I mean, it becomes very, very difficult to teachers apart from those. And that's why most schools will set up a lab, like they might have a VR or a tech lab. The trouble is with that lab approach, rather than integrating it into classrooms, is that it's generally only boys that get to go there. Because boys, want to do the technical subjects or the ICT or the digital tech subjects. So then it becomes a kind of equity issue, I suppose, around, how do we make it much more accessible and interesting to more diverse groups of students. But yeah, I think there's a real, just a massively under-researched area, Florian. And anyone that says they know doesn't know actually what the effects on children will be.
It also doesn't help that the headsets really, up to a certain age don't work with kids because their IPD is too small. And so they just don't adjust well enough. So all they see, they might still find it interesting, but they see blurry images because they have to.
That is true. You know, part of it's hardware, some of it could be the software. We just need to really unpack it, don't we? Like that's a study, that's a large scale study done ethically well. You know,
it's really, really hard to do it as a large scale study though, because the only way to deploy large scale is something like Oculus, and they won't let you work with children. So at least not with something you release large scale. Really problematic. I'd love to do work with children, but yeah, it's so hard to reach them, and then IRB around that, especially if it's remote, is nearly impossible.
I think the way to do it would be to do it with schools.
Yeah.
Like in partnership with school communities, but then the school communities or education departments need to understand the value of it, I suppose. And that is in the future, isn't it? It's not quite yet.
Yeah.
So.
I'm wondering about this comment you made about the school classrooms, you know, having been designed in the industrial age, and how now like we're getting further and further from this as we have these wild new technologies. I was talking to Kyle about this, but like so now that we have VR classrooms, or the VR ability to bring students and teachers together, how will this differ? Like what kind of different things will we be able to do that we, you know, that don't just replicate normal classrooms, but kind of we go beyond normal classrooms? I'm curious if people have thoughts about this. What do future VR learning environments, like group learning environments, look like?
One thing that I think about on this topic was to, let's say, leverage the stigmergy among the, let's say, previous generation of students in VR. So in the VR classroom. So by letting, let's say, having these virtual places to also preserve the previous generation, the time they spent in the VR. So is somehow like leaving the drawing on the table, and you find that as a previous students. So this concept, I think, could be intensified in VR in such a way that can be actually can boost the learning through the let's say previous insight that I have this, I got this in the class. You live here in that place, in that time, a bubble, a voice message, and somebody will find it where in the future. So I think that we can we can build some kind of that concept of stigmergy, and it could be interesting because ultimately it's something that bonds people and also involve emotional responses which lead to better memory and retention. So it's all connected. This is just one idea I got in the past and still not able to fully develop, but it's in the to-do list, in the wish list, more than to do.
I'm envisioning just like graffiti everywhere.
Yeah.
As a learner, I'd like to go to a virtual space that gives me lots of tools to work with people I know and don't know, to accomplish certain tasks and to learn certain things. And it might look like a classroom, but it probably wouldn't. So I could build my own learning environment, and I could have access to learners from, you know, anywhere who'd like to help, you know, be on that learning journey with me and collaborate with me in that. So I'm really that's my kind of vision, which is far beyond the notion of, you know, going to a virtual classroom to learn, I suppose. Does anyone else have any wild ideas about what they'd like to do as learners?
I like the concept of making all learning small group learning. And so even a class of 200, right? You know, if with the right the ability to move around quickly and dynamically, right? An instructor to be able to see into any given zone at any given time. You could really take that a very large class and just break everybody up into very small groups that all had, front and center, view of the lecture material, whatever it is, be able to interact and talk privately amongst each other during that session. I just sort of envision that as being a powerful way to learn that's just not possible right now. At least not easily.
Well, this will be an artifact for the future archaeologists, this particular recording. So you want to put it out there about what you think the future should be.
I think the issue with this is, like if everybody's recording all their classes, you have a huge amount of like long data streams. It's like people's Facebook videos are already really like a ton of data to look through. So it's going to be really interesting how you can like kind of capture meaningful moments so that students can sort of go back into a very specific point in time when something useful happened and kind of skip over a bunch of not so interesting things. So like organizing that data is critical for that.
And I do believe that they will be laughing about us wearing like these massive things in front of our eyes.
Sure.
Oops, Florian's frozen on my screen.
He said something that shouldn't be spoken.
Well, we have 1 more minute left of our workshop. It's been just marvelous. I've just enjoyed every single presentation and our interactions. Are there any last words? Any last words for posterity for our artifact, our VR artifact that we're sending forth? No? Yes? Oh, thanks. Thanks. Yeah. I've had a great time. It's been great seeing everyone and meeting people as well. And hopefully next year we might even be in the same room, in an actual same room. Although it'll probably be a hybrid type thing anyway, but yeah. Okay, well, thank you so much. Hopefully I can see everyone next year in person and enjoy a nice glass of red wine with you. But apart from that, thank you so much for participating and presenting at the workshop.
Everybody.
Thanks all.
Yeah.
Thanks, Julian, too. You keynote, fabulous.
This is my favorite part where we get to see who's actually here.
I love that.
When I end lectures and I'm just sitting there waiting, you weren't actually there, were you?
I'm here, Kyle.
Or in a meeting, a staff
Bill.
meeting. In a staff meeting where they call your name and you kind of quickly try to, click unmute to show you there. See you.